Hello everyone, in this theoretical tutorial number 73, we will explain that even with an ideal switch, half bridges switching will always lose the energy that is stored in the parasitic power supply inductances. Let's first explain the energy losses at turn on. At t equal t0, the current source replacing the load current inject 400 amp into diode D and the parasitic inductor LH, represented by the red dotted arrow. The energy stored in the 22.5 nanohenry inductor LH is equal to 1.8 millijoule. However, since no current flows through inductor LL, the energy is zero. Since the voltage across diode D can be ignored, the output voltage is equal to the positive supply voltage of 300 volt. When the switch is switched on, we transfer 1.8 millijoule of energy from the upper inductor LH to the lower inductor LL. The switch animation shows that when the ideal switch is closed, as LL equal LH, these two inductors form an inductive divider and the output voltage is set to 150 volt, which means half the supply voltage. Since each inductor has 150 volt across it, the current increases linearly in the LL inductor, red curve, and decreases in the LH inductor from 400 amp to 0, red dotted line. The time required to reach 0 or 400 amp current is 60 nanoseconds according to the equation T equal L over U time current I. Until the red dotted current reaches 0 amp, diode D is DC biased. The current in diode D should never be negative, but since the diode needs a recovery time to eliminate the charge stored in the PN junction, during this recovery time of approximately 15 nanoseconds, the current continues to become negative. When diode D is finally blocked, the current in diode D returns to 0 and the switching current to 400 amp, changing the sign of the current slope. Due to the negative current in LL, node E goes to minus 150 volt and node C to 300 volt plus 150 volt, which means 450 volt. Diode D is then blocked with 450 plus 150 volt, which is 600 volt across the diode in reverse for 15 nanoseconds. The energy in diode D is given by the equation ED equal VD time ID time T. Since the average current in the diode is 50 amp, means 100 amp divided by 2, the energy is equal to 0.45 millijoule, indicated by the orange area for 15 nanoseconds. At time T1, the energy stored in LH becomes 0 because there is no longer any current, and conversely, the energy stored in LL is 1.8 millijoule due to the 400 amp. To transfer the 1.8 millijoule from the upper LH to the lower LL, we lost 0.45 millijoule in diode D due to its recovery time. Now we continue with the explanation of energy losses during turn-off. At t equal t0, the ideal switch is closed. The current source replacing the load current injects 400 amp into the closed switch and into the parasitic inductance LL, indicated by the red arrow. The energy stored in the 22.5 nanohenry LL inductor is equal to 1.8 millijoule. However, since no current flows through the LH inductor, the energy is zero. Since this is an ideal switch, the output voltage is 0 volt. During the turn-off phase, we transfer 1.8 millijoule energy from the lower LL inductor to the upper LH inductor. If you look at the animation, when the ideal switch is open, like LL equal LH, and they have the same absolute di over dt, each inductor has 150 volt across it. So node E goes to minus 150 volt and the LL current decreases linearly from 400 to 0 amp. With VLL across LL, see red curve. Node C goes to 150 volt over the 300 volt supply, which means 450 volt, and the LH current increases linearly from 0 to 400 amp, dashed red curve, with VLH across LH. When the switching current reaches 0 amp, node E returns to 0 volt and node C to 300 volt. When the current in LH is 400 amp DC. The energy in diode dZ is given by the equation ED equal VDZ times ELS times T. Since the average current in diode dZ is 200 amp, means 400 amp divided by 2, the energy is equal to 7.2 millijoule, indicated by the orange area for 60 nanoseconds. At time t1, the energy stored in LL becomes zero because there is no longer any current. Conversely, the energy stored in LH is 1.8 millijoule due to the 400 amp. To transfer the 1.8 millijoule from the lower LL inductor to the upper LH inductor, we lost 7.2 millijoule in the DC blocking diode. The 600 volt DC blocking diode and the 300 volt power supply result in 300 volt on both LL and LH, noted in red. The interesting point is, if we increase the blocking value to force 600 volt on both LL and LH inductor, we will reduce the losses from 7.2 to 5.4 millijoule. If we increase the blocking value to force 6000 volt on both LL and LH inductor, we will reduce the losses from 7.2 to 3.78 millijoule. Finally, if we increase the clamp voltage to force 60,000 volt on the LL and LH inductances, we will reduce the losses from 7.2 to 3.6 millijoule, which is exactly the double of the energy stored in each LL or LH parasitic inductance. This means that even with an infinite clamp voltage, the energy losses will be at least twice the energy stored in the parasitic inductance. But with a realistic 600 volt clamp, the energy loss is twice as high at 7.2 millijoule instead of the minimum of 3.6 millijoule. In summary, from the initial state of the low side switch to the on state, we lose 0.45 millijoule in diode D. From the on state to the off state, we lose 7.2 millijoule in the clamping diode DZ. So, to transfer the 1.8 millijoule energy from LH to LL and back to LH, we lose 7.65 millijoule. I want to thank you for your attention. In my next theory seeker tutorial number 74, we will cover translinear circuit, which allow you to multiply and divide an analog current. These circuits allow you to perform basic analog calculations such as square root, inverse, and many others. So see you soon and stay tuned.